Hello, in this video we want to look at section 3 from chapter 18. It's all to do with Coulomb's law, and what this law describes is the force between two point charges. So we've got this force in newtons equal to a constant that was discovered experimentally, and then we've got the magnitude of these two charges, okay, the two that we're comparing, and then the distance between them in meters. Okay. Now the unit on the force is coulombs, or typically we use microcoulombs just because a coulomb is so large. The constant, again discovered experimentally, is 8.988 times 10 to the ninth. Sometimes I've seen it even, and we can shorten it here, but sometimes I've seen it even shortened to 9 times 10 to the ninth, just depending on what level of accuracy we're going for. So we can plug in the constant. If we know the magnitude of both charges, again measured in coulombs, and the distance measured in meters, we can figure out the force between these two charges. Now that can either be force attracting or force repelling. That's why we have the absolute value here. Okay, it doesn't really matter whether the two forces or two charges are attracting each other or repelling each other. We're just interested in the magnitude of that force in newtons. Now you might notice that that formula looks kind of familiar from before when we talked about the force of gravity. Okay, with this equation from gravity we had two masses and still a constant and the distance between those two masses. And now we're just talking about charge, so we've got the charge and again a constant and the distance between them. So very, very similar feeling formulas. If you want, you can go back into the book and read through. They go through comparing the magnitude of these forces, and it turns out that on a small scale, like looking at say inside of an atom or something, this force, this Coulomb force, is much, much stronger. Again, you can read through the entire example in the reading, but 39 orders of magnitude stronger. Now as we kind of back out and get farther away, the force itself doesn't change, but kind of the effect of that force kind of gets canceled out. Gravity is always an attracting force, but this Coulomb force, it's either retracting or repelling, so they tend to cancel out the farther you kind of zoom out, the bigger your system gets. So say planets, the effect between two planets of gravity is going to be much stronger than this Coulomb force, just because we do get that canceling out effect as we zoom out. So we've got a fairly short section, so a lot of this is going to be just examples. For this one, we want to know what factor we have to change the distance between two of those point charges to change the force between them by a factor of 10. Now notice for changing the distance, that's down here in the bottom, so that whatever change we make is going to be amplified and squared. Okay, so if we want a factor of 10, we need to change the distances between them by a factor of the square root of 10. Okay. So, and that could be, if I want the force to be greater, I need to bring the two point charges closer together. So I would take the distance between them and I would divide by square root of 10. If I wanted that force to be an order of magnitude weaker, I would have to separate them and I would take the distance times the square root of 10. And that way I changed the force by a factor of 10. Similarly, if this question had asked if I wanted to change it by a factor of 4, if I wanted to make the force greater by a factor of 4, I would just have to halve the distance between the 2 point charges, and then the force would be 4 times greater if I halve the distance. Okay, just because the distance has more of an effect than the actual charges themselves. Okay, another example here, we've got two charges, and we know that they're half a meter apart, but we don't know what each individual charge is, and we know that the force, either, again, we know that it's a repulsive force this time, and the repulsive force is 0.15 newtons. We want to figure out what each one of these charges actually is. Now they're repulsive, so we know that they're either both positive or both negative, so we're just going to assume they're both positive to make things a little simpler. If I just plug into my formula here, then I've got my force in newtons from the problem, I've got my constant that we can look up, and I'm going to assume, or I'm going to name one of those charges x, and then the other one is just going to be this 8 microcoulombs, so 8 times 10 to the negative 6 coulombs, minus x. So I've got the one that I know, and then I can quantify the other one just by subtracting it from my total up there. And then on the bottom, I've got the distance squared. Okay, so if I go through and I simplify all this, plug in the constant, distribute this x, multiply the 0.5 squared to the other side, divide by the constant, and then get everything on one side, I can get to here. Okay, so quite a bit of algebra between here and here, but it's all very doable, just rearranging, moving things around. I can get to this quadratic formula. Okay, then if I go and I use the quadratic formula, or go to an online calculator, plug all this into a quadratic formula solver, I get to here. So x, one of the charges, I can say is 5.61 times 10 to the negative 7th coulombs, or 0.561 microcoulombs. Okay, knowing that, I can go ahead and subtract that from 8 and find the other one. So my two charges are 0.561 microcoulombs and 7.44 microcoulombs. Again, they're repulsive forces, so either these are both positive or both negative. We don't really know. Okay, but set it up in the formula, and then we do some algebra, and we can find those two charges just based on the information we had. Okay. For this one, again, it's going to be kind of algebra heavy, but we know that we've got two charges, both positive. One is 5 microcoulombs, one is 3 microcoulombs, and they're a quarter of a meter apart. We want to know where can we put a third charge here in the middle so that the net force on that charge is 0. Okay. So again, we're going to use the formula, kind of plug things in. And if we put another charge here in the middle somewhere, another charge Q, we know that we want that force from the 5 microcoulomb side, we want it to be equal to the force from the other side, the 3 microcoulombs. So we're just going to plug into the formula twice and set them equal to each other. This side we've got the distance being x, and on the other side just 0.25 minus x. So I've just plugged into the formula twice, and I want the forces to be equal so that the net force is 0. They cancel out. Okay. Now, one nice thing about the formula is we have it right here. I've got a k on both sides, that constant, so I can divide by that. I've got the charge, so I can cancel that out, so it doesn't matter what magnitude this charge is that we put in the middle. It's going to cancel out. And then I'm also going to just multiply both sides by 10 to the 10 to the 6th so that I can cancel that out and get nice whole numbers. If I do all that, then I can get down to just 5 over x and 3 over 0.25 minus x. So I can get to there, and now I just need to kind of, hang on, these should be squared. My distances should be squared. If I do all that, I can get down to here. So squared and squared. Now I just need to do some algebra on this and solve it. So I'll go ahead and cross multiply, get rid of the fractions. Okay, so I end up here. Now if I want to get rid of the squared on both sides, I can take the square root of both sides. So I'll have square root of 5 times 0.25 minus x and square root of 3 times x. Okay, so we're getting a little bit closer. Now I can just distribute this square root of 5. So I'd have 0.25 square root of 5 and x times the square root of 5. I want to get these x's on one side. So if I add this x square root of 5 to this side, then I can factor out an x, and I can end up with 0.25 times square root of 5 and x factored out, square root of 5 plus square root of 3. And I'm just keeping it all in square roots for now, so I don't have to deal with decimals yet. Divide by this quantity here, and I'll have this divided by these, and that'll be my x, which again is just one of those distances. If I go ahead and solve that, type all this into a calculator, I get my distance 0.141 meters, and just because of where I chose to put my x up here, that'll be the distance from the 5 microcoulomb charge. Okay, And if I were to subtract that from the 0.25, I can find the other one. And can't really see that. If I subtract that from the other one, then I could find the distance from the 3 microcoulomb charge. So again, quite a bit of algebra here, but it all started by just plugging things into our formula that we knew from before. So for most of these, you'll just want to be able to use that formula. Okay, be able to plug in, depending on what we know and what we're trying to find, draw out a picture, plug in what we need to know, and then just solve for the missing parts. Sometimes more complicated than others, but it all uses this same kind of basic formula. Again, very familiar from when we were dealing with forces due to gravity. So, all right, thank you.